Now, let's try to understand the basic data summaries and the visualizations which can help us to explore the data as a first step to come out with different kinds of patterns as well as different identifying the anomalies and outliers in the data, which would be the first step, which would be the basic minimum tool set which each analyst should have. So let's try to see, once any data is presented to us, what is that we can do as a first step is try to understand the basic data summaries and visualization. And for doing this, you don't need to have any kind of a specialized statistical software or analytics software is really not required. Even a simple Excel will do the job for majority of these data summaries and visualizations. However, I would try to cover this entire process using both SPSS as a tool as well as using Excel, and wherever it is not that appropriate using Excel, we'll try to go using the SPSS itself. So let's try to go with one by one. I'll take one data set, and on that data set we'll try to see what all we can do as a part of the basic data summary and visualization process. So remember, this is the task that you would be doing when you are presented with any kind of data. And just to understand, data wise, you may have a few data which is numerical, a few data which is categorical. So let me show the example which I am trying to look at. Here I am trying to look at the housing prices in one particular state in United States, wherein I am looking at the prices in dollars, the square foot of each of the house, the number of bedrooms, the number of bathrooms, how many offers have come for it for a sale, and whether it is brick or not, built with brick or not, and what is there in the neighborhood, probably the east, west, north. Now, in this, if you look at this entire things, these entire fields are categorized as numerical data because is recorded in the form of numbers and it can be measured. Price, square foot. So it's measured, it can be measured. Whereas categorical data, these two, I look at them as categorical data. It is represented in the form of categories and it's not measured. It's yes, no kind of values or gender, male, female kind of values. They are different categories. It can't be measured. And on the other side, I can use a different dimension as well. A continuous data versus a discrete data. Continuous data is numerical. Again, within this numerical, if you see, there are two different categories. Look at only these two. These two actually can have any value. I can even have 1791, 1791.5 square feet, or even the price. I don't need to round it up to 00. So literally almost any value is possible. So that kind of data which is numerical and it can be recorded on a continuous scale. Whereas if you look at bedroom, I may not have 2.2 bedrooms, or I cannot talk about 1.22 bathrooms. So whereas in case of price, I can very well talk to a very minutest of the number, or square feet I can talk to any kind of precision, whereas that may not be possible with respect to the bedrooms and bathrooms. That is what will differentiate continuous data with discrete. Continuous is something in numerical, but it can be recorded on a continuous scale, not just a few different values, but it can be almost any value. Height, weight, they can be measured on a continuous scale. Whereas discrete it assumes only a fixed set of values, typically integers like your number of bedrooms 1, 2, 3, 4. It cannot be 2.12, some such kind of stuff. Similarly, the same thing goes with bathrooms. The number of offers, they can only be counted. They can only be counted, but they can't be measured. Those things come out as a discrete data. So we need to understand in any data set that is provided to us, what is the continuous data, what is the discrete data, so that we can apply the different tools for different kinds of data. Because some of the tools which I apply on numerical data, I may not apply, or they don't get applicable on the categorical data, and vice versa. So I really need to understand the data type so that I can very well use the appropriate tool for analysis and exploration. Now this is what is the data we will analyze. Now probably I may want to identify some kind of the patterns in all these things, so that at a later point I may be interested in developing a model for projecting the price, for predicting the price, right? So for that I have captured the data relating to almost 128 flats as a sample, and using that data I want to do some kind of analysis in it. So it's showing a house ID, selling price in US dollars, its size in square feet, number of bedrooms, bathrooms, number of offers it has received while it is in the market, whether it has brick walls or not, and the neighborhood where it is located. So I have to derive some kind of a useful information out of this data. I want to drive finally what drives the price of this house, which can help the potential buyer decide how much is appropriate to bid for this house. That's at a later point. But as a part of the basic visualizations and summaries that I can look at on this data, we'll see what all steps we can go into. The same data, in fact, I have taken in SPSS also. Now, if you see, these are the values that are there, which are taken from the same data. But here, okay, the brick, the neighborhood. See, in some cases, probably it would be more and more appropriate, even if these values, which are given in the form of a text here, they are captured in the form of numbers, so that we can use them for a later point in time. And if I have to convert these into numbers, one way for me is I'll use a compute or a record into a different variable. I'll create a different new variable. I'll create a new variable using this brick, and I'll call it as brick category. Another new variable I am creating called brick category, wherein I am creating a set of values. Okay, this is the initial screen. So I'll create a value saying if the old value is no, new value make it as 0. If the old value is s, new value make it as 1. Okay, so when I do this, I get a new category getting created. Brick category is a word wherein zeros and ones are replacing nos and s's in a different variable. And for a better understanding, I come to this brick category. I create a label saying 0 means no and 1 means yes. And for a better representation, probably I'll not bother about the decimal. So here I am able to create a no, but this is pointing out to a 0 and yes is pointing out to a 1. The same thing I can do with a neighborhood. I see that there are only 3 different neighborhoods, east, west and north. So I'll also create one more. Probably this time I'll do it with neighborhood, wherein I'll call it as neighborhood category. Right, I'll call it as neighborhood category, and again do the similar kind of a work on the neighborhood as well. If it is east, I'll replace it with 1. If it is west, I'll put a value of 2. I can add something like this. If it is north, I'll put a value 3, and if it is south, I'll put a value 4. So this is the first thing that I do here. Again, though not mandatory, I'm just creating some kind of numerical computation out of this. I'll tell you what we'll do after that. So here I'll say 1 means east, 2 means west, 3 means north, and 4 means south. So we are setting the data accordingly, and even here also the decimals I'll make it 0 to make it look better. Now here the measure, when I am using the measure here, it is showing scale, because these are the ones that are on a continuous kind of a scale. So whichever is continuous, I'll take it as a scale data. Whereas when I look at bedrooms, bathrooms, they are just 1, 2, 3 kind of stuff. Now, the higher it is, there is a pattern. So it's better that I treat this as an ordinal data. Ordinal is the reason means the values, see there, one, it is not a continuous data, it's a discrete data. And within that discrete data, there are two ways of looking at it. In case, see within that discrete data, there are two things. One, where the categories have an order, like ascending or descending kind of order. In that case, I'll call that data as ordinal. Whereas if there is no order, like we have given 1, 2, 3, 4 for east, west, north, south, I could have given it in another way also. There is no logical relationship between the directions. It's not that east is greater than west or west is greater than south. Nothing of that. So there is no order. In that case, it's better that I treat it as a nominal measure. So in SPSS, I can provide within the categorical data, I can very clearly distinguish whether something is ordinal, where an order higher means there is some interpretation to it. Right? Higher and lower has some interpretation. The same logic will go with the offers. So I'll use ordinal for offers also. Whereas per brick, these are string variables, whereas here we have made them as numbers, but still they are nominal in nature. So this is what we have created as a first data set. Now let's start our analysis on this data set, right? First thing, I can do different kinds of things before we get into it. I can do different kinds of things. I can do a summary statistic where I compute the average, median, standard deviation. We'll talk about them, right? And try to make some kind of a basic analysis out of the summary statistics. Then I can do some kind of histogram plotting for the price and see the distribution of the price. How is it, what is the pattern of the various prices, what is the pattern of the various other elements. Now that I am done with, so these two actually go per single variable at a time. One variable at a time, I can do some kind of analysis. And then I can do it in pairs. Probably trying to look at the price versus the square foot. Is there any kind of a relation? Or price versus the bedroom, price versus the number of bathrooms, is there any kind of relation? So that kind of a pairwise relationships I can try to identify, and that I am doing with some tools like correlation, scatter plots, etc. Right, we'll talk about each of them in detail. Scatter plots generally from a visual perspective, they try to see if there is any kind of relationship that is existing between the variables, and correlation is trying to quantify the strength of that relationship between this variable. But yes, just to understand on a broader scale, we'll go in deeper into each of them. On a broader scale, what I am looking at is first analyze each variable separately, whether it is a numerical variable or a categorical variable, or even within a numerical variable, even if it is a nominal or an ordinal, continuous or discrete kind of variables, doesn't matter. We are going to evaluate individually each of the variables. And once we had some amount of information on the variables individually, we will try to look at the pairwise relationship between taking two different variables at a time. So we'll talk about different kinds of measures for doing that single variable analysis as well as the pairwise variable analysis. Right? So that's what we are going to look at as a starting point. So as I said, wherever possible, I'll try to do it in Excel. But in general, using a good statistical tool will really help us in simplifying the understanding process quite effectively. Now, the first thing we'll try to look at is coming out with the summary statistics. Okay, first let me execute the summary statistics in SPSS. Right, so here I'll go to this analyze. In descriptive statistics, I have something called frequency. So I'll use that for doing the summary statistics, but let me tell you, the summary statistics are more and more appropriate only for a scale variables, right? Only for the numerical variables, or traditionally for the continuous, even in numerical, traditionally for the continuous variables, the summary statistics make a lot of sense. Whereas for the categorical data, or even within the numerical data, if it is more and more discrete, it's better to rely on some other mechanisms, which is the basic frequency analysis itself. But when you are looking at scale data, which is numerical or continuous in nature, we can very well look at the summary statistics. The way I can look at that summary statistics is within this descriptive statistics, I use the frequencies. So here I'll look at these two of them. But just for making you understand, I'll add two more, the bedrooms and bathrooms also, to just showcase what is the problem with the summary statistics using for these two. These two will give a good picture from a summary statistics perspective, but these two will have a few limitations. So, but still I wanted to show them, that's the reason I am using this. Then here I will not, here I will go with some statistics. So summary statistics talk about the measures of central tendency, where I look at the mean, median, mode. Then I look at measures of dispersion, where I look at standard deviation, variance, minimum, maximum, range. And I can also look at the quartiles. And the distribution can be known using the skewness and kurtosis. So I'll try to identify all these values. And probably I'll not prefer the frequency tables. We'll talk about the frequency tables slightly later. And if required, anyhow we are going to deal with the histogram. So I'll try to plot the histogram as well. Histogram also is more and more appropriate for a scale data, for a quantitative kind of a data. What it does is it classifies the data into intervals like 0 to 100, 1 or 1 to 100, 101 to 200, some kind of a classification of the data into intervals. and it computes the frequency in each of these classes, and the graph is plotted with this. A simple rectangle kind of a graph is plotted by taking these kind of class intervals. A graph like this is plotted, which is called as a histogram. So this is applicable again for a quantitative kind of data only, not applicable for categorical or a discrete data. So here I am selecting the histogram for that, and if I am trying to run the same, I get a decent understanding for the same. The same thing probably in an Excel sheet also I can very well run, right? But of course in Excel, a lot of these things have to happen on a manual basis. Though there are a few tools that are available, I prefer doing this because of the dynamicness. I can look at the mean, median, mode. We can look at standard deviation, variance, then minimum, maximum, quartile 1, quartile 3, and we can also try looking at the range, skewness, and kurtosis. So let's look at these different values. So again, for each of them, if we have to, let's say we are doing this for these 4 elements. Right here, if I have to do it for these 4 elements, okay, mean comes with a formula of average. Okay, this is the mean for both of them, for all these. Then median comes with a formula of the median itself. So this remains the median in these 4 cases. Then mode, okay, the mode I try to compute coming out to be this, and probably in these cases this happens to be the mode. Then standard deviation, I can very well use STDV. If I, because this is a sample, I'll use it as a sample standard deviation. I'll try to compute the sample standard deviation here. We get some numbers for the standard deviation. We'll interpret them. Then similarly variance, again because this is a sample, I'll take the variance, which happens to be the square of the standard deviation itself. So I square this, I'll get the variance. Then I am looking at the minimum value. So this happens to be the minimum in all these. So minimum of 2 bedrooms, minimum of 2 bathrooms are captured. Similarly, if I am looking at the maximum value, okay, 211,000 happens to be the maximum, and square foot wise 2,590, 5 bedrooms, 4 bathrooms. Similarly, I can look at the quartile 1, which comes out to be the quartile. Within this, I'm talking about the quartile 1, which is the first quartile. Right, within this I am finding out, so this is the first quartile. We'll do the interpretation of it. Then similarly I can use the quartile formula on this data, pointing out to the third quartile. So this is the third quartile for these. Then the range can come out as the, okay, range is nothing but the maximum value minus the minimum value. So working out to these numbers. And then I can even look at the skewness in the data, which is around 0.47 here and probably 0.07, 0.21 kind of stuff. And I can also look at the kurtosis that is present in the data using the Kurt formula, which looks almost 0, and these are the numbers that are present. So this is the summary statistic that comes out. So this is directly coming out in a tool like SPSS. Here I am trying to compute, but of course here also I can get the same using the data analysis, where I can use the descriptive statistics, and here I can look out look out for these four where I'm grouping by columns and the labels are there in the first row. And probably I can point out the output range to this particular I can point out to this particular location, right? So if I am looking at this, I get the same, right? The mean, the standard error, median, mode, standard deviation, kurtosis, skewness, range, all these things are coming out even here as well. But let me tell you, this is not dynamic, whereas this is more and more dynamic. But whatever it is, here our focus is on the interpretation aspect, not much on the generation aspect. Okay, now let's start looking at a few elements that come out for our interpretation. Look at the mean. Okay, so that mean is like on an average. On an average, the price is around 130,000. On an average, the size of the house is around 2000 square feet. On an average, 3 bedrooms, but 3.02 has no meaning. Similarly, 2.44 bathrooms may not have any kind of a specific meaning. Similarly, median is talking about if I arrange the prices in an ascending or a descending order. If I arrange the prices in an ascending or a descending order, the 50 percentile kind of an element, the middle element is having a value of 125,950. So almost like a middle value is around 125,950. Square foot wise around 2000, 3 bedrooms and 2 bathrooms is the 2 bathrooms is the median value. Mode in many cases it may not be applicable to continuous data because this is that particular instance which repeats maximum number of times. For some quantitative data, it may so happen that no value will be repeated at all. In that case, the mode may not have any kind of a meaning. So generally, it is not computed for numerical or a scale quantitative kind of a data. It is more and more applicable to a categorical kind of data itself. Right? Well, whatever is the tool we are doing, we will get the same kind of numbers. Standard deviation 26,800. What does this mean? Probably I can say on an average, right? When I look at the standard deviation, the interpretation comes out as on an average, the price is around $26,868 away from the mean. See, there are a few, now the mean is around 130,000. But let's say if you look at this price, it's not 130, it is almost 16,000 lesser. Even this is 16,000 lesser. Even this is 16,000 lesser. Whereas this is 36,000 lesser. So what we are saying is different elements are lesser by different amount. Now what we are simply saying using the standard deviation is on an average I see that the fluctuation is around $26,868 from the mean. So the higher is the standard deviation, higher is the fluctuation of our data. And if my data is fluctuating very heavily, the predictability will become more and more of a problem for that particular data. It's not that our data is wrong, right? If it is fluctuating very heavily, probably there is a lot of deviation in the data. I have to understand what is causing this deviation. So there has to be a lot more analysis that need to be done on the data. So the price is showing something like this. So this itself, on an average, the deviation is around $27,000. And in another way, if at all, the other way to use the standard deviation is, if at all my data is more and more symmetrical, which means if my prices are more and more symmetrical about the mean means with the mean more or less uniformly distributed on both the sides, showing some, if the histogram is showing some such kind of a pattern which is more and more symmetrical about the mean, what this is saying is, on an average you will find 95% of the values lying between the mean plus or minus 2 times the standard deviation. You will find 95% of the observations lying between these two only. Only 5% of them lie outside it. So if you see here, if 130,000 is the mean and 27,000 is the standard deviation. So what it says is 95% of the prices of the houses lie between 130 minus 54 to 130 plus 54. So 95% of the observations will lie between 76,000 and 184,000. It's very, very rare that the price of the house in this locality, irrespective of any other analysis, I can say that the price of a house in this locality, it's very rare that it is lesser than 76,000 or it cannot be greater than 184,000. Only 5% of the houses will be having a value something more than this or less than this. So standard deviation will really help us in terms of identifying the boundaries for the most probable values of our interval, and which can also tell that the value cannot fall below something or go above something. So that's one interpretation that we get using the standard deviation. So in another case, probably when I'm looking at here, it is also talking to me as 211 is the standard deviation. So on an average, now again the same pattern, but this interpretation will come in handy only if my distribution is more or less symmetrical about the mean. We'll see how we talk about the symmetricality about the mean. But in a simple way, now assuming that it is symmetrical above the mean, so if the mean is 2000 units and the standard deviation is 211, twice of it is 422. So what we are saying is 95% of the houses here will have a square foot 2000 minus 422. The sizes of the houses in this particular locality are anywhere between 1578 to 2422 square foot, and very rarely they are lesser than that particular amount. So that is what is being specified through the standard deviation for any of the variables, and the square of the standard deviation is the variance. So probably there's not much of a different interpretation that we are bringing out of it. At the same time, we are finding out the minimum value and the maximum value, and at the same time, just like the median, we also have a quartile 1 and a quartile 3. So median, see, when we are arranging the data, median is the middle, which is the 50 percentage data value. Similarly, the 25% data value is called quartile 1, 75% data value is called as quartile 3. So this quartile 1 simply tells me that 25% of the houses have price less than this. So it is clearly telling me that 25% of the houses have a price lesser than 111,000. Similarly, Q3 of 148 says, so this is 148. So 25% of the houses are sold for more than 148,000. 25% of the houses are sold for less than 111,000. 25% of the houses are sold for more than 148,000. The difference between the minimum and the maximum values is around 142,000. Right? All these things can come out with a typical summary. And finally, I am looking at the word skewness, which is a measure of symmetricity of the data. To show whether the data is symmetric or not, I will resort to the usage of the skewness. Right, here also if you see 0.473, 0.078, even here we are getting the same kind of observation. See, if at all the data is very much symmetric, we see that the skewness will be very close to zero. Right, skewness is very close to zero. The more and more it is going positive, we say that the data is positively skewed. The more and more it is going negative, I say that the data is more negatively skewed. But with the data which we are working on, getting an exact zero is always a difficulty. Now this is where we'll try to talk about, in a tool like SPSS or any, we will be getting the standard error. Along with the skewness, we will also be getting the standard error of the skewness. Here if we are seeing, the standard error has come out to 0.214. Now simple way for me to check is, if I have to say it's exact zero, because it is not possible, sometimes what we see is it around zero? And what is the way to test is it around zero? For that you take the standard error. So this is the standard error. Double it. So 0.428. So if at all my value is lying between plus or minus 0.428, I equate it to 0 only. I say it is very much close to 0. So here it is 0.473, slightly higher than this. So I cannot say that. So I cannot say that it is as good as a 0. Whereas in all the remaining cases, for square foot 0.078, it is lying within this interval only. 0.215, it's lying within this interval. 0.399 also is lying within this interval. So we can very well say that the square foot, bedrooms and the bathrooms, they are all symmetrical. Whereas the price is not symmetrical. You see, we have got the first pattern. The price is not symmetrical. And the other way you look at it is, if it is symmetrical, the mean and the median should be more or less the same. If you find a huge difference between the mean and the median, even that is an indicator of the non-symmetricality in the data. Here you could see a big difference, whereas here it's a very minute difference between these two. Very minute difference between these two. So here also some small difference is existing. So wherever the difference is bigger, we look at not being symmetric, and wherever it is more or less closer, we talk about the symmetricality being applicable for that data. Straightforward skewness can help me in terms of identifying the symmetric nature of the data, right? Then, so here I can very well talk about the skewness. So I will say in this case that the price is positively skewed, whereas the other elements are more and more symmetrical in nature, right? And of course, the remaining things I'll not cover here. Again, when the need comes, I'll take them up. But this is how for every data that I get, initially I will compute the summary statistics. I'll look at the mean, the median, the minimum, maximum, the quartile 1, quartile 3, standard deviation, and make some basic inferences. If the skewness is greater than, or if the absolute value of the skewness, ignoring the sign, if the absolute, so probably look at it like this, if the absolute value of the skewness is greater than the twice of the standard error of the skewness, we say that it is either positively skewed or negatively skewed. But if the absolute value of the skewness is lesser than the twice of the standard error, then we say that it is almost symmetrical. The data is not skewed, it is more or less symmetrical. And if the data is symmetrical, we have already talked about, if the data is symmetrical, we have already said 95% of the observations, 95% of the values will lie between mean plus or minus 2 standard deviations only. Very, very rare chance that a particular value will fall outside the 2 standard deviations limit of the mean. Right? So these summary statistics can really help us to explore the distributions quantitatively, and they can really help me in terms of comparing across two or more variables. Here I can very well say that square feet is uh, more and more symmetric compared to that of the price. So some such kind of things can quite comfortably be understood. And the quartiles, as we have already talked about, 25% of the prices are below 111,000. 25% of the houses have less than 1880 square feet. 25% of the houses have prices more than 148,950. 25% of the houses have an area which is greater than 2140 square feet. So some such kind of a conclusion can be made quite effectively. But of course, I mean, that's not a conclusion, that's an interpretation. Okay. And we are also saying that this may not make much of a sense. Probably I can't talk about what is 2.45 bathrooms or a standard deviation of 0.726. I can't really make out any sense out of, for number of bedrooms, what is the standard deviation of 0.726. So there will be a lot of challenges if at all I have to do this kind of a computation for a categorical data or even any discrete data also. So as a matter of advice, it is suggested to do the summary statistics purely for scale data which is numerical and quantitative in nature, rather than trying out on a categorical data or a discrete form of a data, right? Then the other way, so what is that I can do? Okay, we'll come to the histogram also. Probably let's complete this. Okay, we have plotted the histogram for each one of them, right? Let's look at the histogram. Histogram is slightly preferred more in addition with the summary statistics, is always accompanied by the summary statistics. Why so? If I am looking at the summary statistics, they are just single numbers, right? Mean, only one single number. Median, one single number. Standard deviation, one single number. Sometimes it becomes very difficult for me to understand the whole data with one single number. That is the typical drawback which people talk about using the summary statistics. It captures only a single aspect of a distribution, some representative of the entire data. But many a times the data can be very, very complex, that one single number may not be a good representation of the entire data, right? Our data might be having more and more outliers in it. There could be many, many anomalies present in the data. Sometimes my data could be a multi-model kind of a data. It's just not one single mode. It can have multiple modes altogether. So the real pattern of the entire data is not fully understood just by looking at the summary statistics. Though they are really helpful in terms of talking about a typical value, the typical deviation, the overall symmetricity of the data, though the numbers are themselves explanatory from these dimensions, understanding the entire pattern of the data becomes very difficult without looking at the visual aspect of it. So histogram is majorly targeted towards visualizing the entire data distribution, and so this is where when we look at the histogram we see that the scales are plotted probably 50,000 to 75,000 or whatever is it, 75 to 100,000, 100 to 110, 110 to 120. So some such kind of scales are being taken, and based on the scale the graph is typically plotted, right? Probably in the Excel spreadsheet also, if I have to go with the histogram, I'll try out for one of them. What we can very well do is I can insert a pivot table for this entire range, wherein I'll in the pivot table I'll go with this, and here I'll point to a location here wherein I'll try to take the price. I'll try to take the price here, I'll try to take the price here, and I'll try to do the grouping of this, let's say by 10,000 each. So I'll get a price grouping something like this, which I can use for plotting a histogram. I'll do an insert column chart which can help me in terms of plotting a histogram. And of course here the values need to be as close as possible to me, right? So which means I will try to do some kind of a formatting exercise here wherein I'll not put any kind of gap. Now once I don't have any kind of a gap, the graph comes more or less like this, representing a histogram. So which means when I'm doing these kind of things in Excel, it is a slightly more manual kind of an exercise. A similar kind of a histogram can be obtained, whereas here it is more and more straightforward. Now this should be more symmetrical above the mean, but here I am not seeing any kind of symmetric nature. Whereas here if you see, yes, see if it is more and more symmetrical, I should see a kind of a smooth bell curve that comes when I am trying to join all the tops. Here I am seeing big spikes. Though here also I am seeing big spikes, again you see the spike is also coming on either side of the mean. So I mean that's where probably this looked more and more symmetrical in nature. About the mean, if you look at, probably the graph is looking more and more symmetrical on both the sides. Here it is not looking that symmetrical. You see some kind of extreme values towards the right. And the same logic here, the more concentration is on these two, but there are a few of them that are falling in this category here. So the histogram can really help us understand the whole pattern of the data rather than concentrating on one single value. So a few things which I have already discussed in context of discrete variables, the average may not be a meaningful way at all. In that case, even even a median is still fine, but in some cases even the median will also have some kind of a problem. But median, at least it's not impacted by the discrete versus the continuous data, and to a large extent it can provide meaningful answers for us, whereas the mean has all chances of providing the value which cannot really help us to make a proper interpretation out of it. But the histogram is more targeted towards that. Probably in a tool like SPSS, I can even within the histogram, I can even show a normal curve on the histogram, which talks about to what extent my data is fitting the normality, the pure symmetricity. Here there is a spike that is, there are 2-3 major spikes, one or two major troughs that are there which are moving away from the normality. Whereas here if we see, yes, two are some spikes that are there here and one more here, probably one here, a couple of them inside. So this is the way it is fitting, the normal curve is getting fitted there. Whereas here, yes, to a large extent we are seeing some kind of normality, but of course here we don't see any, and in some cases there is an excess. Even here it goes, there towards the left side we are not able to see any observations. So an imposing of a normal curve on the top of a histogram can really help us in terms of seeing to what extent the symmetricity exists with respect to the data. Symmetricity is more to look at from the horizontal perspective. How many of them are lying outside the typical symmetric location? How many of them are lying very much inside the symmetric location? So that would be a better assessment of symmetricity and the whole pattern of the data using the histogram. But when I am using categorical data, here I can talk about the categorical data, which is more to do with the bedrooms and bathrooms instead of going, or probably the brick and the neighborhood. Instead of going with the scale data because they are not numbers, I will treat them as a categorical data, and for a categorical data, frequency table is a much appropriate solution. Which means here I will select these two, the brick and the neighborhood. I'll display the frequency tables for them, and graph wise I am not interested in all these things, right? They really don't make any kind of a sense for me for a discrete data. They don't make, or for a categorical data, these things don't make any kind of a meaning. So I'll go with either a bar chart or a pie chart for them. Let's say a bar chart I'm going for them. Okay. So the frequency tables, or I don't need to go with any chart also. I'll go with a frequency table. Now in the Excel also we can do the same thing. Probably I can go with a frequency table per brick as well as per neighborhood. So I'll use some such kind of okay, here if I want per brick and neighborhood, I have to really make a different kind of a table. So no and yes in case of brick, right? A small table I am following in terms of no and s. So I'll use a function like count if. Within this I am trying to count for the no's. There are 86 no's here, and similarly 42 s's are there. Similarly I can talk about east, west, north. South I don't think we have any, but let me categorize that as well. So here also I'll use a count if formula on this neighborhood, pointing it out to east. So there are 45 east in the data, then 39 west, 49 north. So you can do it in Excel also, but the traditional thing is you have to write your own formulas associated with them. Whereas here you have very much got that there is 86 no's per brick and 42 s's. So percentages wise, 67.2 percentage of the houses don't have brick. 32.8 percentage of them have brick walls. Similarly, when I am looking at the neighborhood category, it says around 35% of them have east neighborhood, 30.5% of them are in the west, and 34.4. Along with the numbers, even this gives me the percentage. But here, if I have to do the percentage, again I may have to write a separate formula altogether. Right, I may have to write a separate formula altogether, taking into consideration all these things. So the formula here works out to okay, let me look at the formula. Yeah, the formula is coming out to 67.18 and 32.8. Even here I may have to write it as this divided by the summation of all these. So that's how I'll get the percentages 35.15 and something like this. Probably after that I may have to make use of the appropriate formatting exercise also. So it's not that I cannot do that, but yes, it's a slightly an additional effort in terms of doing it in a spreadsheet. But all of them, if you don't have access to any powerful statistics tool, the same thing can be done using a spreadsheet as well. So it's good for a categorical data. It is used for comparing the frequencies between the individual categories. So here I can directly say, okay, majority of the houses are having east. There is no house which is at south, and almost 67 percentage of the houses are not having any kind of brick walls. Different kinds of quick interpretations I can make from the data by looking at this frequency table for the categorical data. But one thing we have to keep in mind, anything that we are doing on a categorical data, more and more exploration I am trying to do on a categorical data, it needs special attention. And a bar graph is just a visual representation of the same numbers. So sometimes we should not I mean, this can typically show that which one is highest, which one is lowest, just visually at the quick on a quick note. But if there are more number of categories, this graph may become more and more cluttered. So one thing what I suggest is, if at all I am looking at any data that is being supplied, the first thing we have to look out for is the single variable analysis. Each individual variable, right? The step is like this. Each individual variable, first identify whether it is numerical or categorical. Within that numerical, also try to see whether it is continuous or discrete, and whether if it is completely categorical, try assigning it as a nominal variable. If it is more and more discrete kind of stuff, you can call it as an ordinal. Even within that categorical, you can call something as ordinal, especially if there is a kind of logical relationship present. If something is continuous, you can assign it as a scale. And for this scale data, you can perform more and more of summary statistics, as I understanding the mean, median, standard deviation, skewness, quartiles, which can help you to really identify what are the typical values. Then you can even do the histogram for this data, trying to understand the outliers, right, are trying to understand the typical pattern in the data. These kind of things can come out by doing the histogram as well as the summary statistics. But when you are going with the categorical data, either I go with a simple frequency analysis, which is the frequency tables, or I should look out for some such kind of a graphical representation called a bar chart. So this is what will need to be looked at, trying to understand the pattern in the individual variables first before we progress into anything else. And this also, the next thing which I am going to talk about is the box plot, which is again applicable for the entire distribution. This is also more and more appropriate for the numerical data, which is in the form of a scale. Now, this is a plot that actually goes with 5 different measures. Now, if I have to showcase that in Excel, it takes the median, the quartile 1, quartile 3, the minimum and the maximum. This is the 5 different points that are taken in case of a box plot. Box plot is a very powerful tool to identify the outliers in the data. Very comfortably, the outliers are identified in the data. Now, what happens is these 5 are taken. Now, for one single box plot, if I have to talk about, I will try to bring in, let's say, Q1, median, and Q3. We'll talk about these 3. Now, let me bring in Q1, and this is median, and this is Q3. Right? These are the values. Right? So, the first step that goes here is these 3. And based on this, I will also compute what is called as an interquartile range, which talks about Q3 minus Q1. The difference between the Q3 and Q1, we call it as the interquartile range. And based on this interquartile range, we also talk about, so this is a simple interquartile range, and I'll plot the lower bound here. The lower bound for me is Q1 minus 1.5 times the interquartile range. Whereas upper bound is Q3 plus 1.5 times the interquartile range. Right? Q1 minus 1.5 times the interquartile range. And similarly, I can talk about the upper bound as Q3 plus 1.5 times the interquartile range, around 203. Now, this is where, okay, let me do this for all of them. Let me do these calculations for all of them. Now you could see that anything that is outside this lower and upper bound is what we are calling as an outlier. Now you see, with respect to the price, these are the lower and the upper bounds, 55 and 203. Anything that is greater than that, I see that the maximum is much higher than that. So there is an outlier on the higher side. Now this is one way I can very well assess the presence of outliers in the data using this a box plot. Now here this entire thing has to be converted into a plot. What I suggest is there is no direct box plot in Excel. Of course, we can very well create it using the charts. We have to do some kind of modification exercise to create a box plot in Excel. But a straightforward way, if I am using a tool like SPSS, I can very well get into the graphs. In this legacy dialog, I have something called a box plot. And I will do the box plot for all the 4 variables separately. The 4 which I have considered. In fact, I should not do for the bedrooms and the bathrooms. It will not give me any kind of meaningful stuff, so I'll not include them. In fact, I'll do only for the price and the square feet only. For these two ones, I'll try to do the box plot. And I'll do the excluding of the cases variable by variable. Of course, that is more associated only when the data is not present for any of the variables. Now, if you look at the box plot here, yes, in case of price, so the representation is like this. This box is Q1 to Q3. This is Q1, this is median, and this is Q3. The first quartile, the median, and the third quartile. And you see the down and up borders. They are called as the whiskers. Okay, now let me read through the stuff. It draws a box between the first and the third quartiles. This is a box. First and the third quartiles. Marks the median by a line inside that box. Sometimes this is drawn vertical or sometimes it is drawn horizontal. In different tools it is drawn in a different way. But whatever it is, this is a box which is representing the quartile 1, quartile 3, and the middle line inside it is an indication of the median. And along with that, whiskers are being drawn. These two are called as the whiskers, which actually talk about the lower bound and the upper bound, and which are typically drawn using 1.5 times the interquartile range, as I've shown in the Excel sheet. 1.5 times the interquartile range is being used to plot the lower and the upper bounds. So, which is an indicator that based on the typical pattern of the data, these are the accepted values for the typical values. Any value which is outside that has to be treated as an outlier for me, right? So the interquartile range is the distance between the first and the third quartiles, and it is used as a measure of variability. So I'm talking about based on the kind of interquartile range, this should be the range in which majority of my values should lie. If they are not lying, then they are called as the outliers. The data points which are beyond the whiskers are treated by outliers. In some cases, they are marked with circles, and if they are very far away, they are even marked with stars as well. Right? So the box plot, here it is clearly telling me that the record number 104 is actually an outlier in this data. Right? Probably I can see what is that, go back to the data and try to look out for, go to case number 104. Go to case number 104. This is telling me that the price of this is 211,200, which is a more outlier compared to the upper bound that is permitted, which is 203,000. So this is what can be given through a box plot. It can really help me to identify which of the values are outside the range. Now, what will I do with that? Probably I may have to remove that outlier, because my analysis will become more and more biased if I am keeping that outlier as it is in my data. All my data will get, it's as good as saying, okay, if I have 5 observations where the price of a particular article is 10, 10, 10, and suddenly I have something which is saying 1000. the mean gets very badly affected by including this. It's not the typical behavior. It's not, so when I'm doing an average of all these 6, it may come out that the average is around 200. But majority of them are at 10. How can I take the average as 200? But if I remove this, it says that the average is somewhere around 10, which is a real depiction of the reality. So if my data is having some kind of outliers, it's better that I have to remove them to make a much better conclusion. I have to handle that particular data separately. I may have to do some kind of causal analysis on that particular data separately and get to a different kind of a conclusion altogether. And if at all I am getting some such kind of outlier, okay, the other way I look at here, the record number 104, I can say this is coming with respect to price, right? And that too on the higher side. So probably I may say, yeah, this particular seller, he is able to fetch a significantly higher price for his house compared to the others, right? Probably I want to understand what he has really done to go for that much high price for his house. So such kind of a quick interpretation can come out when I am looking at the box plot. And if you really see, the information is more and more similar to that of a histogram itself. Even in histogram, if you see for the price, we must be seeing one price which is very, very odd here. Right? Where I mean, between these two, there is not even a single price, but here there has come out one simple observation. So, I mean, in histogram, probably if I am looking out for the extreme values, there is a different way to look at, but with the box plot, the way I can look at the outlier is a pretty straightforward kind of a situation. So it's always better. Again, all these are the basic steps which I am saying to make your data ready for a very complex analysis. So clean your data, try to understand the outliers that are present in the data using a box plot like this. And in some time, okay, that's all for the individual single variables. If I have to look at, those are the basic minimum steps that are expected. And now in some cases what can very well happen is I may be more interested in looking at taking two variables together, a pairwise relationship between the two variables. So for that again there is a graphical way, right? If I have to really see a pairwise relationship, there is a graphical way and again there is a summary way. For a graphical way, we generally rely on the scatter plot, and for a summary or a numerical interpretation of the same, we depend on a calculation called correlation. And let me tell you, these two are again applicable for a numerical data. So it's better that different pairs of data are compared to understand the patterns between them. So what I can really look at is, I'll try out a few scatter plots. Again in Excel also I can do a scatter plot. First let me complete it here. I will look at a simple scatter plot. Right, I'm taking a simple scatter plot where I'm looking at, let's say, price on the y-axis and square foot I'm taking on the x-axis. Right, so these two I'm marking, and the labeling, if I want, I'll do it with the ID. If at all I need some kind of formatting and all that stuff, okay, the title wise, price versus square feet, right, and whatever, otherwise the default thing will be shown. And again I will display the chart with case labels, but here the case labels are much so many in number, so I don't want to display the same, right? So let me just do this. So the scatter plot is coming out through this mechanism. So probably it's giving me, and even here also in Excel sheet also I can go for this kind of a scatter plot. I'll say insert a scatter plot wherein I am selecting a data price versus square feet, wherein I am taking the X values. I'll take the square feet on the X axis and I will be taking the price on the Y axis. Okay, I have taken the price on the Y axis. Now I'll get a similar kind of a graph even here for this histogram, for this scatter plot. But of course, more or less looking like an upward sloping kind of a graph here. And if possible, I can even see the trend that is present in it by traditionally going into the trend lines and plotting a linear trend line. Okay, there is an upward sloping kind of a trend line that is being displayed. Even here I could see there is some such kind of an upward sloping stuff, which means as the square foot is increasing, the price is increasing, which is a quite normal way for us to understand. The larger the size of the house is, the higher should be the price associated with it, and vice versa. So which is very clearly seen even from this scatter plot. As the square foot is increasing, the price is also increasing. However, there are a few outliers. Probably if you see here, this is one more way to look at. Here there is one wherein the size of the house is much lesser, but its price is much higher compared to the peers. There are a few houses where sizes are higher, but they are priced much lesser compared to this. And similarly, on this extreme border also I could see there is one house which is having a very big size, but its price is much lesser, only to the extent of 150,000. Or a house which is having almost 2,400 square feet, its price is just around 13-14,000, 140,000. So you could very well see some of them which are falling way apart from the traditionally upward sloping kind of a segment. Now the same thing I can think of doing it even for the others. Probably I may think of doing it with respect to price and let's say bedrooms. But it may not make much of a sense. Okay, some kind of an upward sloping is still being looked at. But hardly I see, okay, the house that is having 5 bedrooms, one is available for much smaller price, whereas the other one got sold at a much higher price. But with the discrete set of values, it becomes very difficult to understand the pattern. So it's always advised not to do the correlation analysis or not to do the scatter plot when there are discrete values. Between two scale variables, it is very much comfortable, just like this, which is looking more easy to interpret. Okay, there is a positive relationship between the square feet and the price. As the price increases, the square feet also as the square feet increases, the price also increases, and vice versa. But we can try to, and apart from understanding the relation, we can also try to see which variables are falling from the rest. So probably this one is, I mean, individually there is no problem with it, but when I am looking at it as a pairwise, probably this is falling into a slightly an odd segment. So this value, they are falling much away from the rest, which means I may have to use a different marketing strategy if I have to really target selling these ones. For this, the strategy could be something different. Though it's very small house, I can sell it for a higher price. I have to see what is that kind of a house. But it's a small house sold at a high price. This is a very big house sold at a low price. So I may have to change my strategies for targeting those kind of houses. So that is where the scatter plot can help me in making a quick decision by looking at the pairwise relationship between the variables. Now, just to support it, apart from the scatter plot, see, I want along with the scatter plot, I want a numerical assessment of the same. So this is where, how strong is the relationship? Okay, it's a positive. As the price is increased, as the square feet area is increasing, the price also is increasing, fair enough. But what is the strength? By how much extent, or probably how strongly can I say that that is the situation? Now that is what will come out with the computation of the correlation between the two. The correlation is a measure which talks about the strength of the relationship between the two variables. I'll take the correlation between the price and the square foot, which is around 0.55. The same thing I can do here also. Correlation, I'll go with bivariate correlation, where I'll try to observe the relationship between the two variables, right? And I'll try to compute it. So for the time being, ignore all the other numbers. You just look at 0.553. 0.553 is coming out as a correlation, and just by definition, correlation always lies between -1 and +1. The more and more it is closer to +1, I say that it is a very large, strong, positive relationship. The more and more the number is closer to -1, I talk about a strong negative relationship. So this is one numerical measure which can talk about the strength of the relationship. So it's always better to augment the scatter plot with a numerical assessment of the relationship. Because in some cases, even though we can use the scatter plot, our eye can betray us very much. And the biggest problem with any graphical kind of an interpretation is two different people look at the same graph, their interpretation could be entirely different. So I'm looking at some measure which can indicate the strength of the relationship between the two, and that is what is coming out through the correlation measure. And what we can clearly say is correlation is a degree or the strength of the relationship between the two variables. But one thing we have to appreciate, it only brings out the linear relation between the two variables if they are having some kind of curvature based relation, or probably if they have some kind of a quadratic kind of relation or circular kind of relation, we don't see that correlation is effective in terms of finding the relationship between those variables. It only tries to capture the linear relationship, but at least wherever the linear relationship exists, this tool is a very powerful tool. So that's one more thing we may have to do, especially with the numerical scale variables. Very much essential that I try to measure the relationship between the variables. Now, if at all I have categorical variables, two categorical variables, and I want to see the relationship between them. For our example, I want to look at between the bricks and the neighborhood. Two categorical variables. I want to club both of them and try to see the patterns. So in that case, I'm going with what is called as a cross tabulation. I'm trying to find the numerical summaries using a procedure called as a cross tabulation. Again, I'll go to the descriptive statistics. I have something called cross tabs in that, wherein I'll try to look at between, I'll have, let's say, the brick category in the columns and neighborhood category in the rows. I'll not do anything else. I'll display the clustered bar charts. I am not getting into the statistical aspects right now. I'm just displaying the tables. If at all I have two categorical variables and I want to summarize them into a kind of a frequency distribution, probably you can visualize this cross tab as a frequency distribution with two variables taken together, not a single variable, two variables taken together, I can talk of this crosstab analysis. So I'll just say which one should come in the row, which one should come in the column. I look at both of them. You see here a good display is coming out. Right? Probably if required, I can take it even into the percentage mechanism. Cells wise, I will also try to do the row total, column total and total percentages also, just to understand a little bit more. Okay, let's see this now. Okay, neighborhood category versus the brick. You see here 57.8, 42.2. Right, in East, 57.8% of the houses don't have bricks, whereas 42.2 of them have bricks. And if you are talking about this, out of the total bricks, 30.2% of them out of the total non-bricks. Okay, let's look at it like this. Within the brick category, first let's look at 57.8% of them of the east ones don't have bricks. 42.2% of them have bricks. Whereas in the west, it's again 59-41, almost similar to this. Whereas look at the north, 84.1% of the houses don't have bricks. Only 15.9% of them have bricks, which is quite significantly different from these other two categories. So probably one interpretation that is coming out for me, that in the north, there are a majority of the houses without brick walls. Very few houses have brick walls in the north. One significant thing that came out. Now let's look at within the brick category. Okay, within the brick category, where there are no bricks, 30.2% of them are in the east, 26.7 are in the west, and 43% are in the north. So no brick walls are majorly found in the north, whereas the brick walls are majorly found in the east. Some such kind of a quick computation is coming out for us overall. So this kind of a cross tabulation can help us in doing the assessment in this way. Probably even in the graphical way, we could see a huge gap between the brick category no and brick category S in case of the north, whereas the gaps are more or less similar in case of east and the west. So this cross tabulation can really help us in terms of graphically visualizing or even table based visualization of pairwise abnormalities that are present in the data. Right. So this way we can try to assess two different variables and see what is the kind of relationship between them, what is the kind of difference that is existing between those two groups, what are the patternistic differences that are arising between the two groups can quite comfortably be measured through this cross tabulated frequency analysis and an associated clustered bar chart. And if I really want to come out with a measure, a correlation number, logically speaking, the regular correlation which we have used earlier, it was more and more appropriate for a scale data or a numerical data. Whereas if I have to look at the correlation for categorical data, I have two other measures called as Kendall's tau and the Spearman's rho. These are equivalent correlation measures. See, rho is actually called as a rank correlation. These are different correlation measures which are more and more applicable to categorical data. So what I can really think of is I can try to use the correlation between the brick category and the neighborhood But instead of using the Pearson, I'll go with Kendall-Stauby or the Spearman correlation, Spearman's row, Spearman correlation coefficient. Now here also I could see in case of Kendall-Stauby it is minus 0.219, whereas here it is minus 0.23. It is hardly any kind of a big number. So they are more or less independent. There is no pattern that is existing between the two variables, right? The more and more pattern existing between the variables, there you can say that if one of them is marked to a no or else, the other one will be in the east or the west. So that is not coming out straightforward. Typically, these two will become more and more handy if I am dealing with ordinal data, not with the nominal data, right? Whenever we take up an ordinal data example, we'll try to use the Kendall-Stauby and Spearman's row. But just to showcase that the Kendall-Stauby and the Spearman's row, probably I'll use the same with the bedrooms and the bathrooms. I want to know if the bedrooms are higher, the bathrooms are also higher or not. So that's where I want to look at the Kendall-Stauby. Okay, it is saying Kendall-Stauby is only 0.37, whereas Spearman's row is around 0.39. Though there is a positive relationship between the two, it's not very much close to 1. So it doesn't mean higher number of bathrooms means higher number of bedrooms or vice versa. There could be some kind of difference. They are to some extent independent. But of course, it's not they are purely independent. If the number is very close to 0, I can say they are very much independent. But there is some kind of a positive relationship that is existing between the two. So whenever the data is given to us, before making any big statistical conclusions and predictions and decision making on it, first we are trying to spend more amount of time in terms of exploring the data, first with single variables, then taking two variables together, whatever is the tool that we are working with. First with single variables, then taking a pairwise relationship between the two variables, and based on these we are trying to assess what the quick ballpark patterns in the data, outliers in the data, so that we can take appropriate action and then take this entire data towards making our decisions in a much more appropriate fashion, right? So we have to make sure that all these things are taken care of once you see any kind of a data in any tool. Here tool really does not matter. The process of operation which you are performing is very much important for us, right?